Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this second video class of DIP, we will see the human visual system and different elements of digital image processing. In the first introductory video class of DIP, we understood what is digital image processing and few applications of digital image processing. So remember, everything is there in the name. So let's start with the name human. Human means we, the people. Visual means one that is connected with seeing. And system means the structure, right? So human visual system means structure of vision of humans. And elements means different parts or components or block diagram, you can say, of digital image processing. So remember, in our previous video lecture, we saw that for humans, our eye acts as a camera or image capturing device, and our brain acts as the computer for processing, right? Now you may have question in your mind that what is the need to study the human visual system? Because if we consider that human visual system is the best in the world, then if we can create a replica of it for computer, then it will be the best system for digital image processing. So this will be the contents of our class. So let us start with the structure of human eye. So see, human visual system has three components: the human eye, the nerves that carry the signal from the eye to the brain, and the brain itself, right? But what is important for us is the human eyes. So we will study the human eyes. See, we human beings are visual creatures. Out of the five senses that Almighty God has gifted us, the sight or our eyes is the sense on which we depend most. So this figure is of the cross-sectional view of a human eye. The front of the eye is covered with a transparent surface which is called cornea. The inside of the eye has got retina, which is composed of two types of photoreceptors, the rods and the cones, right? So now see, again, everything is there in the name. Why the names rods are there or cones are there? Because the rods have the shape like the rods and the cones have the shape like the cone, right? So the rods are like this in shape and the cones are like this in the shape. So each retina has 6 million cones and around 120 millions of rods. These rods are important for black and white vision in dim light. These rods allow us to discriminate between different shades of dark and light. And the cones are responsible for color vision and sharpness of vision in the bright light. So in moonlight we cannot see color. Why? Because only rods are functioning in the moonlight. So this phenomena is known as the scotopic vision or dim light vision. So the rods are responsible for scotopic vision and the cones are responsible for photopic vision. Now the nerves containing the retina leave the eyeball through the optical nerve bundle to the brain, right? Now see how the image is formed inside the eye. When light falls on any object, the light gets reflected and the light entering the cornea is focused on the retina by lens that changes shape under muscular control to perform proper focusing of near and distant objects. So as we do focusing using camera lens, similarly we do the focusing for the eye using the eye lens, right? Now as the front part of the eye is curved, it bends the light, creating an inverted image on the retina. You can see here the image on the retina is inverted, and this image is going to the brain, but the brain eventually turns the image right way up by again inverting it, and we see the image same like this. So the distribution of rods and cones are shown here. At a point near the optic nerve called fovea, the density of cones is greatest. You can see here near this fovea, the density of cone or cone cell peak is occurring. Due to this, it is the region of sharpest photopic vision. right? The rods are more near 0 to 40 degree. As the image extends further to 60 degree, even the scotopic vision becomes dim, right? This also becomes dim because the rods are less. The photoreceptors are connected to the nerves, and these nerves combinedly leave the eyeball as optic nerve. The region from where the optic nerve leaves the eyeball has no rods and cones, right? Why? Because there is no retina over here, and this is called the blind spot. You can see this is the blind spot, right? Blind spot. Here you can see the blind spot, and here this one is the blind spot because here it is leaving at this particular degree in between 0 to 20 degrees, right? So why it is called blind spot? Because we cannot see an image that strikes the blind spot, and normally we are not aware of this blind spot, right? But let us try one experiment for realization of this blind spot. Draw two letters DNA on a piece of paper approximately 3 inches apart. Close your right eye and focus on the letter A using your left eye, and slowly move the paper near to your face. At some particular distance, the letter D will disappear. Initially, you will be able to see the letter D also along with A, but you have to focus on A. But at some particular distance, the D will disappear, and this happens due to the blind spot because the D is falling on the blind spot. Conversely, cover your left eye and look continuously at the letter D. You have to see cross, right? If you are closing your left eye, that means you have to see D from your right eye. So you will see the word A at this time, and now increase the distance between the screen or your eye. At some point the letter A will disappear, right? And this happens due to blind spot. You can even try this by pausing this video. Pause the video or freeze the screen and try out this. You will find out the realization of blind spot. Getting it? Let's go ahead and understand the contrast sensitivity. Now see, the response of human eye to changes in intensity of illumination is non-linear. Let us perform an experiment. Okay, take one glass plate and illuminate it from the bottom with some constant illumination I. Now the observer is asked to look on the glass plate from the top. At the center of this plate, the intensity of illumination is increased from I to say I plus delta IC, the change in illumination, right? So now the observer is asked to observe whether he or she can observe or detect this increase. If the observer cannot detect the change, the intensity is further increased by another increment of delta IC. And this procedure is continued till the observer detects the difference, and this is known as the just noticeable difference. So this ratio of delta IC to I is called the Weber ratio, and this is different for different person, and therefore it is said that the response of human eye to changes in intensity of illumination is non-linear, right? So low Weber ratio means that even a small variation of delta I was detected by the observer, right? And that is a good thing. And a high Weber ratio implies that large variations were required for the observer to notice the changes. Okay, that is delta IC plus delta IC and so on. Hence, a low Weber ratio means that the observer has a good contrast sensitivity, and a high ratio means the observer has poor contrast sensitivity. So at proper illuminations, the Weber ratio of most of the people is constant near 0.02, and from this graph you can see that the Weber ratio is large at very low and very high levels of light intensity. Why? This is quite obvious. Why? Because our discrimination quality reduces when we are in a room that is not well lit with light. At the same time, our discrimination quality also reduces when there is too much of light. The intensity of light is very high or very low, we cannot discriminate it, and the Weber ratio is very high. But for most of the persons, the Weber ratio is approximately 0.02. Getting it? Okay. So that is contrast sensitivity. Let's go ahead and understand brightness, adaptation and discrimination. See, the range of intensities to which the human visual system can adapt is enormous, of the order of approximately 10 raised to 10. But at a given point of time, our eye can only observe a small range of illumination, approximately 40 to 50, right? So this figure shows the range of intensities human system can adopt. When illumination is low, that is scotopic vision, right? Remember, dim light vision means scotopic vision. When illumination is low, the scotopic vision plays a dominant role, whereas for high intensities, photopic vision is dominant. So as can be seen from the figure, the transition from scotopic to photopic vision is gradual, and at certain levels of illumination, both of them play a role, even the scotopic and the photopic. So we can say that the dynamic range of human eye is enormous, but the eye cannot operate over the entire range simultaneously. Remember, it can only detect some small range of illuminations, right? And this is known as brightness adaptation. So you can even try out this brightness adaptation yourself, right? You stare at the sun for few seconds and the eye adapts itself to the upper range of intensity values. Now look away from the sun and you will find that you cannot see anything for some time. Why? Because your eye takes a finite time to adapt itself to the new range, right? Similarly, you would have observed that when the power supply of your home is cut off in the night, everything will be pitch dark immediately and nothing will be seen for some time. Why? Because your eyes was adapted to light, right? But gradually your eye will adjust to this dark level and you will start seeing some visible things even in the dark, right? So this is brightness adaptation. Let's go ahead and understand the Mach bands. See, these Mach bands are named after the Austrian physicist Mach. Okay, he gave a set of grayscale strips starting from pitch dark up to very light gray. So now each of these 8 strips have uniform intensity within the strip. This is complete dark, this is less dark, this is still less, this is still less, and this can be seen if we place our hand on all of the other strips and observe only one strip at a time. You can try it out yourself. But when we look at all the 8 strips together, the visual appearance is such that each strip looks darker at its right side than its left. Okay, here it looks more darker as compared to here, or even if you see this, here it looks more darker as compared to this, right? So why this happens? This happens due to the Mach band effect or Mach effect. So the actual intensity are changing like this abruptly, right, like a staircase, whereas the perceived intensity tends to overshoot at the right hand edges. Let us go ahead and understand simultaneous contrast. So see this figure. Here each of the square inside have the same intensity, but as the surrounding level of each bigger square is different, okay, this is white, this is gray, this is black, the small squares do not appear equally bright. Here this appears more bright as compared to this, and here it appears less bright as compared to this and this. Why? Because the intensity that we perceive are not actually the absolute values. So here the contrast perceived is relative to the nearby successive or simultaneous value of the bigger squares, right? So this is known as simultaneous contrast. Getting it? Okay, let's go ahead and see different optical illusions, right? See, our visual system or our eyes plays a lot of interesting tricks on us. See this particular figure. Here actually there is no white square, okay, but our eyes consider this as a white square due to the shapes which are kept in this particular manner, okay. Similarly, here there is no round shape, but our eye will feel that there is a white round over here. See both these lines, which one is larger? You will say that this is larger. No, actually both of these lines are of the same size, but as this is open outside, this one looks larger as compared to this one. See these lines, so you will feel that these lines are not parallel. This line, or this line, or this line, or this line, these are not parallel, but in fact they are parallel. These do not appear parallel due to the cross hatches that are present, and this is also optical illusion, right? You will be feeling that this figure is moving, right, or is animated. No, it is not animated. You look at one particular circle, any one particular circle, let us see this, and keep on looking it continuously, the figure will stop moving. So this movement is due to the optical illusion. Now out of these two orange circles, which one is larger? you will say that this orange circle is larger. No, both are of the same size, but as this larger has smaller circles around, it looks larger as compared to this one, as here there are larger circles surrounding it. Okay, so these are known as optical illusions, right? Let us go ahead and finally see different elements of a digital image processing system. So these are different elements of digital image processing system, or you can say the block diagram of a digital image processing system. It consists of a problem domain or an object which is sensed by sensors. It has got image processing hardware, image processing software, computers, mass storage devices, image display and hard copy devices, right? With reference to the sensing, two elements are required to acquire digital image. The first is a physical device that is sensitive to energy radiated by the object, right? And such physical device is a camera, you can say, right? And second is a specialized image processing hardware is required that will be converting that particular signal or image that is analog into digital, right? This image processing hardware consists of a digitizer plus hardware that performs other primitive operations such as arithmetic and logical operations, which performs arithmetic such as addition and subtraction and logical operations in parallel to the images. The computer is a general purpose computer, or it can range from a PC to a supercomputer depending on the application. Image processing software consists of specialized modules or programming languages which are used by users. Mass storage is a very must in image processing applications. An image of size 1024 cross 1024 in which the intensity of each bit is 8 bit requires a 1 megabyte of storage space if the image is not compressed. So image processing applications falls into three principal categories of storage: the short-term storage used for digital processing, online storage for relatively fast retrieval, and archival storage such as disk and hard drives. The image displays used currently are mainly color displays that are an integral part of the computer system. Hard copy device are the devices for recording image, including laser printers, inkjet units, digital units such as optical and CD-ROM, etc. Right? And networking, it is almost a default function in any computer system in use today. Why? Because of the large amount of data inherent in the image processing application. So the key consideration in this particular networking is the image transmission bandwidth, right? So these are different blocks of image processing system and their interconnection, which I have explained in short in the next slide. So that is all for this video lecture. In the next video lecture, we will study different steps or fundamental steps in digital image processing. Thank you very much.